Hello everyone, this is Dr. Lennon, and today we're going to look at integration by parts. So remember the idea here is that we want to look for a way to kind of reverse the product rule. So this is the reverse of the product rule for differentiation. And it takes a little practice to see what we want to pick, but the main formula here is that if you have something set up as the integral of u times dv, this can be rewritten as uv minus the integral of v times du. And I'll show you some examples with why this is the case, and then maybe at the end we'll talk about why this formula is true. But in order to actually use the formula, you don't really need to see the proof. It actually takes a little bit of practice what quantities we want to pick to be u and which ones we want to pick to be dv. Those are generally your choices. We want to pick something to be u and something to be dv, and then we want to rewrite using the right-hand side of this formula. So we'll just go through a handful of examples. So the first one here, well, why don't we just, so we'll say integrate using the integrate by parts. So all of these are going to be by parts. Maybe there will be some sub parts of them that we'll do by substitution, but the main idea for all of these is to just integrate them by parts. So let's say we have the integral of 14x times e to the 2x dx. So what you can do is you can try to pick, so we have two main factors here. We have 14x, the polynomial quantity, and then e to the 2x, the exponential quantity. So we typically want to think of what is getting simpler when we take the derivative, and if one of the things is maybe getting more complicated when you take the antiderivative. So it turns out 14x gets simpler when you take the derivative, but more complicated when you take the antiderivative, while e to the 2x will be about the same, because if you would differentiate just e to the 2x, you would get 2e to the 2x, whereas if you would integrate it, you would get 1/2 e to the 2x. So for this one, the choice is we want to let u be equal to 14x, so that that one gets simpler when we differentiate, and dv we want to pick to be e to the 2x. So then we differentiate with respect to both variables, so we would say du is the derivative of 14x would be 14, but we're also going to put a dx there since we're using du in the right-hand side of the formula above. And then that if we integrate both sides, we would get v is equal to, like we said, 1/2 e to the 2x, or e to the 2x over 2. And then what we want to do is we just want to take our integral, and that is going to be equal to 14 times e to the 2x over 2 minus the integral of v times du. So that's going to be our 14 times our e to the 2x over 2, and then we also have the dx. So then this simplifies to 7 e to the 2x over 2 minus the integral of 7 e to the 2x. And then the thing that we have left over, 7 e to the 2x, is just one of our simple integrals that can be done using one of the basic integration formulas. Oh, sorry, I left out an x. When I was doing u times v for the first quantity, it should be 14x, not just 14. So I left that off. So I'm missing an x in both spots. So this was 14x, which makes this 7x e to the 2x over 2. Excuse me, again, and then dividing by 2 got rid of the 2 in the denominator. 14 over 2 is 7x. So this is just 7x e to the 2x, and then integrating the next one, we'll be dividing by 2 now from integrating the e to the 2x. So we'll get 7 e to the 2x over 2, and then we can have plus our constant of integration. Okay, so let's work through another. Let's say B. Let's say we want to integrate by parts, and maybe this one is a definite integral, meaning we have some limits, which also tells us that our final answer will be a number rather than a function or expression. So in this one, there's not a, we haven't learned a antiderivative formula for the natural log of x. So again, it makes sense to pick u to be the polynomial part here. No, excuse me, it makes sense to pick u to be natural log of x because we know the derivative of the natural log is in fact 1 over x, whereas we don't have an antiderivative formula yet. But we'll actually learn how to do that using integration by parts as well. So we're going to pick u to be the natural log of x here, and we'll pick dv to be x to the 4th. So then our du will be 1 over x dx, and our v will be x to the 5th power over 5, and then we just plug into that formula. So we want to multiply u times v, so that's going to be x to the 5th over 5 times that natural log of x, and then we want to subtract the integral of v times du. So that's going to be the integral of 1 over x times x to the 5th over 5 dx. And then from there, what happens? Well, we have, and again, there's still limits here. We're just going to plug them in at the very, very end once everything is once we've removed all the integral symbols. So we've got x to the 5th over 5, natural log of x, minus this integral from 1 to 2 of x to the 4th over 5. The x in the denominator cancels with the x in the numerator. And then to take the antiderivative of the final remaining expression, you're just going to add 1 to the power, so that'll be x to the 5th. You'll divide by another 5, so that'll be x to the 5th over 25. So our final thing here, we have x to the 5th over 5 times the natural log of x, and then we're subtracting x to the 5th over 25, and that is from 1 to 2. So then we want to plug in both of those values. So I went ahead and did that in the calculator, so we get about 3.156 minus negative 0.04, and that comes out to be about 3.196. So that is the final answer there for part B. Okay, so let's go through maybe 4 more. And again, if you remember, if you are looking at the additional homework, I've done some more examples there by parts, but probably you wanted to review this video first before going to that. Let's look at the integral of, say, x e to the 2x dx. So again, here we want to pick u to be x and dv to be e to the 2x. So du is pretty simple here. Du is just dx because the derivative of x would be 1. And then taking the antiderivative of e to the 2x, that would be e to the 2x over 2. So then our integral formula just becomes u times v. So that's x e to the 2x over 2 minus the integral of v times du. Well, in this case, v is just e to the 2x over 2 with that dx. So that is, again, a basic antiderivative formula. We're just going to be writing down the first quantity. There's no integral there. And then for the second one, the antiderivative, we're going to be dividing by another factor of 2. So it's going to be e to the 2x over 4. And then we can add our constant of integration because this one was not a definite integral. What if we added another layer to that one? Maybe we said, okay, what about if it were the integral of x squared e to the x? So this is kind of an interesting one because we'll see something kind of similar happen. Well, this one, it turns out you can't just do in one step. We're going to have to repeat the integration by parts process twice. So in this one, we're going to make the same designation. The polynomial part is going to be u, and the e to the x is going to be dv. And so du, in this case, will be 2x, and v will just be e to the x. So then look what happens. Let's write our integral down. So this is the thing that we're trying to solve is the integral of e to the is x squared times e to the x, and then this will be equal to uv, so that's x squared e to the x minus the integral of v times du, which is 2x e to the x Well, the interesting thing that's going on here is we can pull that 2 out. Oh, no. So we don't need to pull that out. In this case, we just need to do the integration by parts again. So let me rewrite that. So we have x squared e to the x minus, and then we can take a 2 out, and we have the integral of x e to the x dx. And we just did that in part A, right? We saw that the integral of, that was x e to the 2x. So this one is slightly different. This is x e to the x, so we have to, on this part, perform integration by parts again. So we have to do it a second time. So for that integral, we have 2 times the integral of x e to the x dx. So for that one, we would say u would be equal to x, and dv would be equal to e to the x. So du would be dx, and v would still be e to the x. So this integral would become, we'd have our 2 times uv x e to the x minus the integral of v times du, which in this case is just e to the x dx. So this is really just 2 x e to the x, and then the integral of e to the x is just e to the x, so minus 2 e to the x. So we can plug that back in right here. So that's kind of this part. So this is the second integration by parts. That will go in above. So this final answer would be x squared e to the x minus, and then we have to subtract both of those things, minus 2x e to the x minus 2e to the x. And then we can add our constant of integration at the end, as usual. And write this as x squared e to the x minus 2x e to the x plus 2e to the x plus c. And that would be our final answer. So for that one, it was a little bit tricky because we had to do integration by parts twice. And if I were smarter, I would have made the previous example just x e to the x so that we could just appeal to the result from part C. But essentially we did that again in the little bubble that I drew. Okay, so let's go ahead and move on to part E. So let's say we want to do, so this is going to be pretty similar to part B, but again, just a touch different. So we're going from 1 to 2, and we're doing x squared natural log of x. So remember from that one, it makes sense to choose the u to be the natural log of x and the dv to be x squared. So du is 1 over x dx, and v here is just the antiderivative, so add 1 to the exponent, x to the third, and then divide by that number. So now that we've got those parts set up, we're ready to do the integration by parts. So our integral here is u times v, which is x cubed over 3 times the natural log of x. You know, you can write that all as one fraction if you want. It's up to you. I don't know. It kind of looks a little messy. So x cubed times, I don't know. I'm just writing this like a mess. So sorry. X cubed natural log of x over 3, multiplying the u and the v. And then we want to subtract v times du. So we're going to get that 1 over x. That's going to cancel one of those factors of x in the numerator from the factor corresponding to v. So we get x cubed natural log of x over 3 minus the integral of x squared over 3 dx. And then we can go ahead and finish off our problem. Again, remember that we did have limits here. We had limits from 1 to 2. So at the end, we are going to have to plug that in. So we have x cubed over 3. And then what is the antiderivative here? Well, we have to add 1 to the power again. So it's going to be x cubed. and then we're dividing by another 3. So the 2 3's in the denominator, 3 times 3 make 9. And then we're going from 1 to 2. So let's plug those things in. So we've got 2 to the third power natural log of 2 over 3 minus 2 cubed over 9 minus, and then plug in 1. So 1 cubed natural log of 1 over 3 minus 1 cubed over 3. So let's just simplify this. So this comes out to 8 natural log of 2 over 3 minus 8 over 9. And then the natural log of 1 is 0, so that first term in the second part drops out, and then we're going to be adding 1/3. So you can do this in your calculator if you want. Sorry, there is one slight error here. It's 1 cubed over 9 at the end, not 1 cubed over 3. So this should be minus 1 cubed over 9. Then when you distribute the negative, it's plus 1 over 9. So this comes out to about 1.07 when you put it into the calculator. Okay, let's look at one last integration by parts example. Let's say the integral of the natural log of x dx. So as we mentioned, this has a very simple derivative formula. The derivative is 1 over x, but we don't have an antiderivative formula yet. And the trick here is use integration by parts. So how do we do that? Well, we think of this as the integral of 1 times the natural log of x. And we're going to let, again, u be the natural log of x, and we'll let dv be equal to 1. So that would make du equal to 1 over x dx, and v will just be equal to x. So then when we apply the integration by parts formula, we get uv, which is x natural log of x, minus the integral of v times du, which is x times 1 over x dx. So we actually have x natural log of x minus the integral of 1 dx, and we know the integral of 1 is just x. So we get x natural log of x minus x, and then plus a constant of integration if you want. And that is the integration formula. One thing we can do there to check, so if we differentiate x natural log of x minus x using the product rule, we should get just the natural log of x. So I'll leave that for you to check, but if you differentiate that quantity, you should get exactly the natural log of x back. So yeah, so that's it for integrating the natural log of x. So just finally, let's talk about why the integration by parts formula makes sense. So this is just like a sketch, but let's recall what the product rule was. This is not a very formal argument, but it will give you some intuition why this is the case. So the product rule said if you take the derivative of two factors, uv prime, you get u prime v plus uv prime. This is the differentiation, or the product rule for differentiation. Product rule for derivatives. So, what would happen if we rewrote this as uv prime, and then on both sides we subtracted u prime v, so we have we have minus u prime v is equal to uv prime. And then if we integrated both sides, we would have the integral of uv prime minus the integral of u prime v, and this would equal the integral of uv prime. Well, the integral here will cancel out with the derivative. Those behave like inverse operations. That's the fundamental theorem of calculus part 1. So now we would have uv canceling out with the derivative operation. Then we'd have the integral of v, and then u prime, instead of u prime, we'll write it as du. And then this will equal the integral of u times dv. So if you look at what's going on, this is exactly the formula that we were looking for. This is the integration by parts formula. So you really see it does in fact come from the product rule for derivatives. And what we're doing is we're picking a u and a dv for two things that are multiplied together that we don't know how to integrate, and then we're simplifying it, where hopefully we've chosen it in such a way that our integral of v times du is a simpler integration formula than the one that we started off with. So that's a quick sketch of why the integration by parts method makes sense. But anyway, give it a shot and let me know if you have any questions on any of the homework problems. So this is Dr. Lennon signing off.